In this video, we are going to cover the definition of consistency. So let's start with the definition. We say that an estimator, so let's call the estimator beta j, and it depends on the sample size, n. So we say it's consistent and it's a consistent estimator of beta j. So beta j is a true value here. If for all epsilon that are positive, and epsilon can be as small as we want, the probability that the distance between our estimator and the true value, so the probability that this distance is bigger than our epsilon goes to 0 as n goes to infinity. So you can also say that this distance will become very small when the sample size becomes very large. So graphically, here we have our estimator beta jn, and here we have various sample size. So let's say we have a very small sample size with 2 observations, and we try to estimate what beta j is, and with our first sample we find this value. For our second sample we find this value. Third sample, etc. So we have a lot of different samples, and we have a lot of different value, and you see that this value is very large. Here in the middle we have the true value, beta j. Now let's take a sample size that's a bit bigger, let's say 4. We again estimate with several different samples, and we see that it doesn't go as far as for small sample size. Now let's go to a much bigger one, 10. Starts to become more accurate. 100. Now they are very close to the true value beta j. So this looks like it's consistent because when n becomes bigger, we get closer to the true value. You see a kind of pattern here. Be very careful. Do we have a probability of finding beta j here equal to 0? No, right? We can still find the beta j that's pretty far from the true value. It's just that this probability will be very, very small, right? 0.000, etc. 1, for instance. So we can write this long notation here, probabilities that the distance between beta j hat and beta j is greater than epsilon. We can write it differently to save some space. So usually for econometrics, we'll write it, we call it the PLIM, probability limit. So PLIM beta j equal the true value. Or sometime you'll also see, and that's the more statistical way of writing it, beta jn converges in probability to beta j. So be very careful. We defined before unbiasedness. And here we have consistency. There are two very different concepts, right? Unbiasedness doesn't imply consistency, and consistency doesn't imply unbiasedness either. Let me give you an example for that. So let's say we want an estimator of the mean. So you know the very famous estimator 1 over n sum of xi, and we want the mean or the expected value of xi. So this is called x bar usually, but instead of having this we have plus 1 over n. is this unbiased? Well, let's check that. So let's call this estimator x tilde. X tilde is the expectation of basically x bar, which is this part here, plus 1 over n. And here we can split the expectation, so we have the expectation of x bar plus the expectation of 1 over n, it's 1 over n. So we have mu x, the expectation of x, plus 1 over n, which is different from mu x. So here it is biased. However, it's consistent, and you'll see some rules later about the probability limit that will show that this is consistent. What happened is that here the bias 1 over n will go to 0 as n goes to infinity. So here we have something that's biased but consistent. Now let's take another example, and we want again to estimate the expected value of x, that's equal to mu, and we take an estimator that's just x1. So we have several values for x, right? We have x1, x2, x3, etc. And we just take the first value we have. What is the expected value of x1? Well, it's the expected value of any x, it's mu. This estimator is actually unbiased. Will it be consistent? Well, here, even if we have a very large sample with several x's, so we have x1 to, let's say, x a million, we just look at the first value and we say this is our estimator. Well, the plane of x1 is just x1. Doesn't change with the sample size. And this is different from mu. So it is not consistent. So here we have first an estimator that's biased, so that's bad, but it's consistent, that's good. And the second example, we have an estimator that's unbiased, which is good, but it's not consistent. Well, you will see that most of the estimator we use are both unbiased and consistent, which is the best case.